Hello everyone. In this video we're going to talk about the cables in suspension bridges, right? For example, like the Golden Gate Bridge. So have you ever wondered what's the shape of this cable? What is the length of the cable that you need? How much is tension at any point in the cable? Where is the maximum, or how much is the maximum tension in the cable? So for example, if you want to have something like that, how much cable do you need, and what kind of material and what thickness of cable you need so it can tolerate the weight. So here we look at this picture. This is a bridge, and this is the suspension part of it, really. The cables that are attached to 2 points between two stands, basically 2 fixed points. And we have the load W, or W of X in general, that is applied at each point at distance X. You have the load intensity W of X, right? So this is the load intensity. This is load per unit of length. And it can be variable, it can be constant, and we want to analyze this kind of cable. So here we look at an infinitesimal part of this cable at location X, where the beginning is at X, the end is at X plus dx. The tension on the left side is called T. The angle of the cable with respect to horizontal axis is theta. On the right side, the angle changes to theta plus d theta, and the cable tension changes to T plus d T, because you know tension in the cable is not fixed, and the angle of the tangent to the cable is also not fixed. So they changes, and we show these changes by d theta and d T, and the amount of vertical load on that small portion of the cable is going to be W times dx, where the length of this is dx approximately, and W times dx is what? The amount of load. Remember, W is load per length, so you need to multiply it by the length to get the total force. And again, this dx is approximately the same as the length of this, although there is some y variation as well. But since this dx is very small, I can say that the length of the cable is almost the same as dx, so it's w dx. And now we look at the equilibrium for this element. So some of the forces along x is 0, some of the forces along y is 0. Along x, you have what? You have this force times cosine of that angle minus this force times cosine of this one, right? That's equal to 0, because that's the only thing I have. And this is what you can see here. If I take one of the forces on one side, take the other to the other side, this here is what? This is basically summation of the forces along x equals 0. That's this equation. Along y direction, you have this T plus dt times sine of this angle, right? Remember, this is the cosine, this is what? The sine. The sine component of this minus the sine component of this T on the left side, so that one minus this one, is equal to what? Is equal to this vertical load downward W dx. And again, if you write it, you're going to get this one. So this guy is what? Some forces along y equals 0. So now what would you do? Here, you're going to expand this sine of theta plus d theta. You expand it, and you expand cosine of theta plus d theta. Well, you know that sine of a plus b is what? It's going to be sine of first one, cosine of the second one, right, plus cosine of the first one, sine of the second one. Now, d theta is a very small angle close to 0, so cosine of it is practically 1, and sine of it is the same as itself. So if you expand that, it's just going to be sine theta plus cosine theta d theta, which is this guy. Also, cosine of theta plus d theta is going to be cosine theta cosine d theta minus sine theta times what? Sine d theta. And again, this guy is 1, and this guy is the same as d theta. So that should be cosine theta minus sine theta d theta, which is this one. So all I did here is I expanded those sine and cosine of the two angles added. So I get now this guy on the right side. Now, can I simplify this? Yes. How can I simplify that? Well, if you look here on this left side of this, what can I do? Here there are two terms and there are two terms, right? So if I multiply this, what do I do? You get four terms. It's going to be t cosine theta plus dt cosine theta, and then minus t sine theta d theta, and then minus dt sine theta d theta. This is equal to t cosine theta. Now these two cosines for both sides would cancel. This term has two small terms multiplied together, while these two other terms only have one small term. So for example, if we say this d theta or dt are of order 10 to the negative 3, then this guy is going to be like 10 to the negative 6. So this guy is much smaller than these two terms. So from this guy, we practically what? We practically neglect it. We practically don't consider it in comparison to these bigger terms. So all would be remaining is d theta cosine theta minus t sine theta d theta equals 0, and that is what you can see right here. Also, on the top one, again, you have two terms and two terms. You have four terms, right? So let me expand this one as well for you. So this is going to be like t sine theta plus t cosine theta d theta, and then plus dt sine theta, and then plus dt cosine theta d theta. This is equal to t sine theta plus w times x dx. Sorry. So again here, this t sine would cancel. This term again has two small terms compared to these two guys, so this one we also neglect. Therefore, you get this one equals w dx, and that is what you can see over here. So far we got to what? We got to these two important results. And now let's continue to the last part. By the way, I just did a little bit cleaning. It was just too much out of order. So now this term here, this bottom term, I can write it as d cosine d of t cosine theta equals 0. Why? Because you know this is a product. D of a times b is d of a times b, which is dt cosine theta, which is this guy, plus d plus first one, which is t times d of cosine theta. D of cosine theta is what? Negative sine theta d theta, which is this guy. So I can rewrite that whole thing as this one. And top one, this whole term, again, can be written as d of t sine theta equals w of x. So now I'm down to these two simplified, beautiful equations. D of t cosine theta is 0, which means whatever this t cosine theta is, d of it is 0, means that guy does not change. It's a constant. So that t cosine theta, which does not change, I call it a constant t naught. I just introduced this notation t naught. It's a constant, so I call it just t naught. Okay? And if t naught is t cosine theta, therefore t is t naught over cosine theta. And now I plug that into this top equation. So it becomes what? If you look at this top equation and divide both sides by dx, it becomes d of t sine theta over dx equals w, right? You can write this top one as what? D of t sine theta over dx equals what? Equals w. Now for that t, I replaced it with what? With t naught over cosine theta, correct? Remember that t naught is a constant. I can take it out, and sine theta over cosine theta becomes tangent of theta. So it becomes t naught d over dx of tangent of theta equals w. So now I can divide both sides by t naught and get this. And now this tangent of theta is the slope of what? Is the slope of the rope, correct? Theta is the slope of the tangent line. So tangent of theta is the slope, and slope is dy over what? dx, like this. So if I plug instead of this guy dy over dx, what do I get? Derivative of dy over dx, which is going to be second derivative of y, is going to be what? W over t naught. So finally I get down to what? To this last equation, and this is the differential governing equation for the shape of this rope. It tells me what is the shape of the rope, what is y as a function of x in terms of the force or the load intensity, and in terms of this constant T naught. This T naught is an unknown, but we can find it from the bridge conditions. So this T naught we have to find. Also, we need to find y as a function of what? X. Okay? But this is the governing ODE. So now that we found it, let's apply it to a suspension bridge, a real example. So let's say this is a suspension bridge here. As I said, something like, for example, Golden Gate. The total span is L, and the height of the tower point compared to the very bottom point of the cable, I call it H. So here, the origin is not at the ground. The origin is what? At the very bottom, lowest point of the cable. And this is H, that is L. Good? Now, remember that your second derivative of y with respect to x is what? W over t naught. So we start here. Now, in this case, we assume that this w here is what? A constant. It is not necessarily what? A constant, but here let's say we apply a uniform load what? Over the entire bridge. So if that w is constant and t naught, remember, is a constant, so it's gonna be the dy over the second derivative of y with respect to x is entirely a constant. So now I integrate both sides. So the first derivative of y with respect to x, which is the slope, is gonna be wx over t naught plus a constant. You integrate it one more time, your y is gonna be a quadratic function of x, right? Now here, not only we have to find these two constants c1 and c2, remember I also need to find what? T naught. So in this y versus x equation, there are three unknowns to be found. Where do I find them? Well, here at the origin, what do I have? X is 0 and y is 0, correct? So here x is what? 0, and let's write it this way. Let's say y at x of 0 equals 0. Also, the slope is 0, which means what? Dy over dx at this origin is also 0. If I plug those two, it means both of these constants are what? 0. So your y is just this term, that's the only term, and your dy over dx is just this term. Now, how do I find t naught? Well, I have another condition, and that is this point. Here, at x equal L over 2, y is h. So y at x equal L over 2 is what? H, as you can see. And if I plug it here, I can find my what? Plug y and x here, I can find my t naught. So this is that constant t naught that we talked about it. And if I plug this t naught back into the y equation, this is going to be your y as a function of x. You look at it, it's a parabola, and you can see clearly that at x of 0, y is 0, at x of 0, the derivative of y is 0, and at x of L over 2, the y is h. So this parabola, this parabolic equation of y versus x, it matches all of the boundary conditions, right? So far we found the shape of the cable. The shape is what? The shape is parabola. Good. Assuming that w is what? Constant. If it's not constant, then we have to integrate this w, which is a function of x, so that y is going to be more complicated. But here, for simplicity, we go with constant w. Good. So this is the shape. That's the first thing. Then what? Then we need to find tension in the cable, which is very important. Remember, T is what? T naught over cosine theta. So here, that's what we have. That is T naught. And cosine theta, as you know from trigonometry, is 1 over square root 1 plus tangent squared of theta. So if I bring that in the numerator, you get this. And tangent of theta, remember it was dy over dx. Remember that? Tangent theta is dy over dx, and dy over dx is what? Wx over t naught. So I replace it here. And if I simplify that t naught and this t naught, this here is going to be what? Is going to be my tension in the cable. You see, it does depend on x. At x of 0, which is at the origin, it's this minimum tension, which is equal to T naught. But as I get away from the origin, T grows with x. And at this point or this point, you get what? The maximum tension, which is T naught squared plus WL over 2 squared, where T naught is this constant. Okay, so this is the maximum tension in the cable. You can use that for the design of the cable. This is the maximum tension in the cable. You need a safety factor to be multiplied by that, and that will tell you what material to use for the cable and what diameter to use for the cable, so it doesn't basically fail. Finally, how much is the length of the cable that you need from this A to B as a parabola? Well, for that, we use the formula for the length of any arbitrary curve, which is a square root of 1 plus y prime squared, the integral from a to b. Now, this is symmetric, so I just calculate half of it from x of 0 to L over 2 and multiply by 2. And for dy over dx, I replace that linear function, so this is going to be my integral. Now, this integral is typically not a simple integral to calculate analytically, so here we use the expansion. For here, I use the expansion of 1 plus x squared, okay, and I use the expansion of that, and that gives me this infinite series. Now, the good thing with this infinite series is when this h over L, this ratio of h over L is small, and we can show that as long as this ratio is less than 1/4, 0.25, then this guy will easily what? Will converge to a fixed number, and so I can add more terms, but the contribution of each term gets smaller and smaller. So then after a few terms, basically I have almost the entire S, so I don't need to calculate this forever. Okay, and again, all you need is to expand this 1 plus x to the n, or 1 plus x to the 2 in general, and then take the square root of that. But it's better to use n, and the reason is x squared to the n, basically like this. Let me write it. So it's like this one. And that's what you have here. N is 1/2, basically, is that the square root. If you use the Maclaurin expansion for this function, right, or Taylor expansion, and so write this whole square root as a polynomial. Of course, it's going to be infinite polynomial, but if you integrate it, you get this guy. And again, if you add just a few more terms, then you can easily get the total length that you require. And you just need this condition to be satisfied. And for most bridges, the height h is what is way less than this L, right? If you look at, for example, the Golden Gate, if we just search for h and L, we'll see that this L is about 1280 meters, and the total height is like 200 and something. So h is less than that total height. So this is like 227 meters. So this H is probably about 200 or less. Okay. And clearly 200 over 1280 is for sure less than a quarter. Okay, so the series will converge and you can find the total length of the cable that you need. And again, with this one, you can find the maximum tension, so you can select the cable. Now, of course, the design of a suspension bridge like Golden Gate is way more complicated than this, and there is not a single cable here. Inside this, there are tons of cables, not just one or two. Okay, so the design is way more complicated than this, but here just gives you some basic theory to calculate. If you want to do a suspension bridge, you want to know something about the cable, then this can be helpful to you. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.